Hello everybody and welcome to the next lecture of 6837. Today we're going to continue our discussion of geometric computing for computer graphics by talking about coordinates and transformations, essentially how to compose a scene together out of its component parts. So really, I would say the more accurate title for a lecture like this one and our next lecture is something like bookkeeping for computer graphics. You know, how to keep track of all of the different coordinate systems that objects live in and link them all together. So the basic motivating task here is, let's say that I used the past lecture to model a bunch of objects in a scene, like, I don't know, a bunch of things sitting on my desk in front of me, my keyboard, my laptop, and so on. Now I need to compose my scene together. Right, so in order to do that, I want to translate, maybe rotate, stretch, scale all of the objects that I just modeled and put them all in one coordinate system, like the coordinate system of the table. And doing all of that is essentially going to be a major task in bookkeeping, which is going to be what we talk about today as well as in our next lecture. So to get started, I thought I'd start with kind of a goofy philosophical question here, which is to ask, where is the origin? Now, this is a goofy question, but if I give you a particular scene and I ask you how to model it, a totally reasonable question that you'll have to answer as an artist putting the scene together is, where should I put that special point 0, 0, 0? Now, probably if I were modeling this little scene with rocks and grass, I might put the origin, I don't know, at an interesting point like here. It doesn't have to be relative to the camera, so it doesn't have to be like right in the middle of the scene. But now maybe I've modeled this interesting object and some of the stuff around it, but I decide that I want to incorporate it into a larger scene. You know, I want to put that pile of rocks in a big scene of grass with clouds and so on. Did the origin move? I don't know. I mean, you could imagine that modeling this big scene, maybe I want to put the origin in some more central location. Or now maybe I step back even farther and I model that little grassy scene all the way from space. Probably in each one of these settings, I might choose a different location for the point 0, 0, 0. But from the perspective of that little pile of rocks, having the origin be like the center of the earth probably would be a pretty frustrating setup for an artist. And that's really what's motivating the contents of our lectures for today and next time, is this idea that maybe I model that pile of rocks in its own coordinate system, and then if I need a coordinate system for a larger scene, I specify the motion of that entire sort of chunk of my scene, maybe a few different objects clustered together, all moving at once. So I end up with kind of a hierarchical setup. I would say a more natural example maybe is modeling a car. You know, I model all the different parts of the wheel relative to the center of the wheel. Then I place all of those parts moving together as one wheel unit relative to the car. And then maybe I move the car as it drives through the scene. And each one of those things happens in its own coordinate system. And that's what's allowing us to have a pretty complex set of movements in graphic systems without a huge amount of headache in terms of specifying them. So the basic observation here is that we rarely use absolute positions in real life. That is, there's no such thing as the origin of every 3D scene out there in the world, but rather it's sort of an artistic or an engineering decision that depends on the details of your system. And moreover, you might get it wrong. And so in computer graphic systems, rather than like, you know, if I'm going to model a vase sitting on a table, I have to model the vase in the coordinates of the bottom of the table because I know I'm going to put all of these things together. A more typical thing to do might be to maybe hire an artist to model a vase in its own coordinate system and then have somebody else composite it all together. And that really motivates the use of not absolute positions, but rather relative ones. So we're going to cover machinery for a different approach, which is called hierarchical modeling. And this is going to keep track of many different coordinate systems and their sort of relative motions between one another. So the different coordinate systems that we'll talk about include maybe the scene, the location of the camera, in this particular scene, maybe the car, the driver, their arm, their hand, and so on. And essentially what happens in a computer graphics system, in fact, it's often built into your hardware, is to traverse the hierarchy of the scene up and down really, really efficiently so that essentially the humans that are modeling these things can work in the absolute coordinates, but the rendering system can work in, the humans are working in the relative coordinates, but the absolute coordinates that are needed to actually render the scene can be obtained really, really quickly. So when we talk about coordinates, I think when you take linear algebra class or geometry, pre-calculus, whatever, we get a little bit sloppy. In particular, we think of coordinates as just big tuples of numbers, like an x, a y, and a z. And in some sense, if all you're worried about is drawing parabolas on graph paper, that's good enough. But the reality is that these tuples are kind of meaningless without specifying a coordinate system. So as an example here, let's consider, a point which is roughly maybe 1 unit to the right and 2 units up. So maybe my coordinate is 1, 2. Well, if I just give you that tuple 1, 2, and I don't tell you how to interpret it, that could mean two very different things depending on the coordinate system. So for example, I would obtain this blue point if my coordinate system were these two axes, right? The kind of bluish axes. But if my coordinate system were the red axes, I would get a completely different point on the left-hand side. Now, this might feel like a pedantic point, but it's actually a really central concern in the design of computer graphics systems. So like if I hand you a triangle mesh, then chances are I modeled it in a different coordinate system than the one you're going to model your entire scene, right? So if I have a scene that's composed of lots of different triangle meshes, B-splines, subdivision surfaces, all that good stuff, in addition to just remembering the locations of all the points on these objects, I also need to remember what coordinate system they're in and how to translate between them as I put my scene together. Okay, so in today's lecture, we're going to cover a lot of different objects that I think all get muddled together in your linear algebra notation, but especially in today's lecture, we're going to relax a little bit in the future. We'll try to be very careful to distinguish between a lot of different objects that all could be plausibly described using just like a tuple of numbers. In particular, we'll talk about points. Points represent locations in space. We'll talk about vectors, which are more like movement, velocity, displacement, force, and so on. We'll talk about normals, which are orientations, so they're like vectors with unit lengths. And all three of these objects, these are geometric objects, right? The way that I've described them isn't like, a point is a set of three numbers, but rather I'm trying to think of it like a point is a location in space. And then there's a question of how to deal with these objects mathematically, and all of them are dealt with mathematically using coordinates, right? Just tuples of numbers. But how to interpret that tuple of numbers depends on the type of object that you have. Okay, so hopefully we'll get that point by the end of today's lecture. In fact, in today's lecture, we're going to follow some notation. I think it was originally proposed in Gortler's textbook on computer graphics that tries to distinguish between points and vectors and so on. In the remaining lectures of 6 to 837, we probably won't bother doing this. It's a little pedantic and frankly tricky for your instructor to remember all the different tildes versus arrows. But at least for today's lecture, we're going to do that. And it's always acceptable for you to use that notation on your homework. Okay, so we're going to start easy today and then build up in complexity and sophistication. But if there's one message that you can get out of today's lecture, it's essentially what's drawn on the screen here. And that message is that points and vectors are different, okay? Now, both of these objects are described using tuples of numbers, right? I might say that I'm at position 1, 2, 3, or I might have those same three numbers used to represent a velocity vector. But there are a lot of differences between these two types of objects that I think we all know intuitively, but sometimes we don't call out specifically. So, for example, the zero vector has a really fundamental meaning. Right? The zero vector means that there's no motion or no force or no displacement. Whereas there's not really such thing as a special point whose name is zero. Moreover, we can add vectors to one another, right? It makes perfect sense to add velocities or displacements. But adding points really doesn't make sense. Like adding Boston to New York City because those are two locations gives me what? I don't know. I mean, I could answer that question philosophically, but I don't think that there's a standard mathematical solution to that equation. Okay, and so that distinction is going to be really critical for us. And we're going to see that when we develop a very specific way of doing our bookkeeping with coordinates, namely we're going to use something called homogeneous coordinates, that the distinction between points and vectors will kind of fall out automatically. In fact, this is one of these overlooked super cool aspects of the math that we do in the computer graphics world. Use another example. So if I want to render a moving car, then points would describe the locations of the different elements, the steering wheel, the car, and so the wheels, and so on. But vectors can describe things like velocities, displacements, and so on. And so, for example, if I translate the car, like the car is driving along the road, the point locations change, but other things like the distance between the wheels, or the displacement is probably a better word, really doesn't. So again, there are many different ways that you could make this distinction. Another one might be that vectors tend to describe relative things and points tend to describe absolute things. Okay, so I'm going to be really careful, at least I'm going to try to be really careful about using the proper terminology today when making a distinction between points and vectors. And the reason to do that is, of course, we don't just carry around these objects, but we actually try to edit them. So if you remember your linear algebra class, the main object that we have for transforming points and vectors is a matrix. Now, a matrix has at least two different roles. I would argue that there's like millions of different roles for matrices, depending on what area of computer science or math you're in. But in today's lecture, you can think of this in two different ways. So, for example, you could think of a matrix as acting on points. So, for example, you could cook up a rotation matrix that takes a car that's facing north and rotates it 90 degrees so that the car is facing east. So, in other words, as you apply that matrix, the points kind of move with it. Or there's a dual way to use matrices, which is to change coordinates. So in that case, maybe the car stays put, but I want to describe the position of the car relative to a person standing on the sidewalk rather than relative to the stoplight or something like that. So in that case, the location of the car doesn't change. What changes is the base point and the axes that we're using to view the car. Now, both of these things get described using matrices, and they're sort of hard to distinguish between one another. So again, this is one of these cases where I think the formality can get in the way. You should think of a matrix as just sort of like a function in your code, right? It takes in points, and then when you multiply them by the matrix, it outputs other points. And essentially you should keep track of what your matrix is actually doing. And then I think it's almost like programming instead of linear algebra when you're trying to compose these objects together. So our goals for today are to define coordinate systems and talk about how to change coordinate systems so that we can traverse this hierarchy of different coordinates in our next lecture. We'll also talk about how to transform objects, like rotate them, translate them, and so on. And the whole time, we're going to try and keep really, really clear the distinction between points, vectors, normals, and their coordinates. Now, those first three objects, just to reiterate one more time, these are geometric. They're not just tuples and numbers. They represent spatial things. I don't know why my laptop keeps putting these little lines here. Whereas this last thing, this is actually where you have numbers. And so even though at the end of the day, your OpenGL code is going to contain a bunch of coordinates and they're going to represent points, vectors, and normals, we're going to try and separate the representation from the underlying geometric object. This is a bit of a pedantic point, but it's one that's worth doing, at least for one lecture. Okay, so our basic plan, which I guess more or less follows that previous slide, is first to define vectors and points. We're going to talk about a really powerful tool in computer graphics world known as homogeneous coordinates. This is going to allow our linear algebra to do not only linear transformations, but also affine ones and transformations that include camera projection, which is really, really critical. Remember that camera projection is like taking objects in the coordinates of 3D and putting them in the coordinates of your 2D camera. So there's effects like foreshortening. And then in our next lecture, we're going to talk about transforming normals. So for instance, you might remember from geometry class that a normal vector is a vector that points 90 degrees to a surface. Now let's say that I apply a matrix to my surface to stretch it out. The question we're going to answer at the end of our next lecture is how to transform the normal to that surface. And I'll give you a hint. It is not as simple as multiplying the normal by the same matrix. That's a common mistake. Okay. Unfortunately for you guys, the basic tool for this lecture is going to be even more linear algebra. So in case you thought you were done with it after we finished talking about curves and surfaces, I regret to inform you, you have many more lectures to come that are all going to use the same machinery. The positive news is that if the last couple lectures were a little bit abstract, you're going to continue to get a lot of practice with different instances of linear algebra that come up in our everyday computer graphics life. And I guarantee that it'll become more natural for you with the more practice that you get. So the basic object that we deal with in linear algebra is something called a vector space. And remember that a vector space is just a set of things equipped with an addition and a scalar multiplication operation, right? So for example, the set of n-dimensional vectors, right? They allow you to do things like take two vectors and add them together. Or I can take a vector and I can scale it by a scalar. Hopefully you guys remember that a scalar is just a fancy word for a real number or number. And there's a special element in a vector space, which is the zero vector. And this is going to be the object that sort of abstracts a lack of displacement or force. Okay? So a vector space, at least a finite dimensional vector space, can be represented using a basis. So given a bunch of basis vectors bi, I can take any vector in my vector space, we'll call that vector v for short, and I can write it as v is equal to a weighted sum of the basis vectors bi. That's the definition of a basis, is a set of vectors for which this is possible and unique. So we're not going to talk about infinite dimensional vector spaces, at least for now. It actually will come up a tiny bit when we talk about anti-aliasing much later in this course. But in this course, mostly our vector spaces are just 2, 3, and actually 4-dimensional. And that's because, again, we're dealing with, 3D computer graphics. And we'll see later in today's lecture that adding a fourth coordinate actually can make certain graphics tasks a little bit easier. So here I've given you an illustration on the bottom of the slide of vector scaling and vector addition. So for example, 2 times the basis vector b1 can be obtained by taking b1 and stacking it on itself twice. And then if I want to, I could add b2 by displacing b2 to the base point of 2 times b1, and then composing all of these things together, and that's giving me the vector v. Okay. So as a little more linear algebra review, hopefully you all also will attend the linear algebra review section that's going to be led by our TAs. Let's say that I can write a vector v in a 3-dimensional vector space as the sum at the top of the slide. So v is equal to c1 times our first basis vector b1 plus c2 times our second basis b2 plus c3 times our third basis vector b3. Then I can write in sort of compact notation by thinking of the basis vectors as sort of like the columns of a matrix. And remember that matrix vector multiplication goes like this. I'm realizing, again, I'm gesturing into the camera and it might get flipped left to right. But remember that I read matrix vector multiplication by going left to right on the first guy and top to bottom on the second. So actually, you can think of this product here as exactly the same as the expression that we wrote on the top of the slide. Now, this notation that I'm giving you is the tiniest bit curious. Now, in particular, this matrix on the left-hand side, we're going to call it B. Typically, when you think of a matrix, you think of the coordinates of B1 as the first column, the coordinates of B2 as the second column, coordinates of B3 as the third column. That's perfectly fine, but it actually turns out not to matter, that it's actually enough to just think of a matrix, a basis matrix, as a thing that collects together basis vectors, one per column, the way that I've written it here. And you don't even have to think about it like coordinates, right? If I think of, just following that matrix vector product formula here, I'll get the expression on the top, and I never had, for example, to write B11, B12, B13, and so on. So this is going to be a bit of a pedantic point, but if you like this sort of philosophical approach to linear algebra here, this basis matrix is containing B1, B2, and B3. You can just think of the columns as the basis vectors. It doesn't actually have to be their coordinates. If that doesn't make sense to you, it's perfectly fine to think of them like coordinates. I'm not terribly worried about that. In any event, we're going to use a particular shorthand that I've given you at the bottom of the slide here. Now you can see where I'm going to try and be super careful with our notation to distinguish between coordinates, matrices, and vectors, where vectors are these abstract geometric objects and coordinates are tuples of numbers. So in particular, if I think of B as this basis matrix whose columns are vectors, they might be the coordinates of vectors or they might be the geometric objects themselves. Then if I take B and multiply it times C, where C, we use this boldface font, really does mean a tuple of 3 numbers, then I get this vector V. So again, this is just a fancy way of writing the expression that we had at the top of the slide. Now, you guys should take some time to really understand and parse this notation. It's not totally standard. I doubt that your linear algebra course bothered to do this sort of thing. But the basic point is that we're trying to distinguish between vectors as a geometric object and their coordinates in a particular basis. Okay. So now that I've probably totally confused you with notation, I'm going to keep layering it in there. In particular, now we're going to talk about how to modify vectors using linear transformations. So hopefully all of you guys remember from your linear algebra course that a linear transformation L is a function that acts on a vector space, and it satisfies 2 really critical properties. Namely, if I apply my linear operator to the sum of 2 vectors, like v plus u, that's the same thing as applying my linear operator to v, applying my linear operator to u, and then summing the result. In addition to that, if I take a vector v and I scale it by a scalar alpha, that's the same thing, and then I apply the linear operator to that. It's the same as applying the linear operator to v and then scaling the result by alpha. Now, all of you probably remember the most common example of a linear operator or linear transformation is matrix vector multiplication. Incidentally, notice that these 2 properties above imply that any linear transformation applied to the 0 vector has to give the 0 vector back. Why is that? Well, let's think about it. So the 0 vector can be thought of as the scalar 0 times the 0 vector. Well, by the second property, that's the same thing as 0 times L of the 0 vector. But anything times 0 is the 0 vector. This proof kind of looks vacuous, and that's because it is. But it's kind of nice to know that you can get this property from the 2 properties on this slide. One more little piece of notation. This thing, you can read it out loud as maps 2. So you can think of this little arrow as sort of talking about the map that takes v to L of v. So it's just like nice notation for a transformation. Often linear, but in different areas of math, it doesn't have to be. Okay, so we often confuse matrix multiplication for linear functions, and that's because the two are intricately linked together. So let's see if we can derive that property more carefully. Let's say that I have a linear map L, and I apply it to a vector V. Well, I can take any vector V and write in a basis. So like I can write V as some linear combination of my basis vectors Bi. And now let's apply our properties of linear functions to simplify this object a little bit. So first of all, remember that a linear operator applied to a sum is the same thing as summing the linear operator. So I can write that this is equal to the sum over I of L applied to Ci Bi. And remember that I can pull scalars out of linear operators. So that's the same thing as the sum over I, Ci L of Bi. Okay. So why bother doing that? Here's the thing. What specifies my vector V? Well, in effect, what specifies a particular vector in a vector space is nothing more than its coordinates, right? These numbers C. The basis is a property of the vector space itself, not a property of the particular vector. But in order to specify my linear map, well, this expression is telling me that the only thing I really need to know is actually a finite set of vectors. I need to know L of B1 to L of, I don't know, Bn, if n is the dimension of my space. And if I give you just this set of vectors, this completely determines the action of L. Do you see that? Because essentially I can take a vector V, any vector V in my vector space, write it as a combination of my basis, plug in the expression that I just wrote down, and if I know this finite set of vectors, I now know L of V. This is kind of miraculous. I mean, I think we all neglect it in linear algebra class, how super cool this property is. But essentially, it's telling you is that if I know the action of L on a finite set of things, namely the basis vectors, then I actually know the action of L anywhere. That is a really special property of a linear map. Okay, so let's look at that in nicer PowerPoint notation here. So again, the basic point here is that a linear map is really determined by its action on the basis vectors for the space. If I want to notate this algebraically, applying some of the things that we've learned in the previous slides, let's say that I think of my vector V as this matrix vector product, right? So these are the coordinates, and these are the basis. Then I can think of the action of L as leaving the coordinates alone, right? Notice that they're still here, but acting on the basis vectors, right? And this is just a slick version of the notation that we've been developing in the last couple of slides. Okay, so now you guys can start to see how all of our notation is going to interact in a nice way. So let's talk about linear maps that map from one linear space into itself. Note that that doesn't have to happen, right? There are many linear maps that go between different spaces. So for example, if I had a matrix that isn't square, it could go from R5 to R7 or whatever. But let's say that that isn't the case. So I have a map from one space into itself, and that map is linear. Well, in that case, a really cool thing happens. It's kind of like turtles all the way down here. Namely, remember that my linear map is really determined by its action on the basis vectors Bi. But those are also vectors, and they're vectors in the same space. What does that mean? Well, I mean, this is a big pile of symbols, but at the end of the day, this really is just some vector. And remember that the point of a basis is that I can take any vector and I can write it in my basis. So I'm going to take L of Bi and I'm going to write it in the BI basis. And I know I can do that because the BI's form a basis. So in particular, that is going to lead us to these weights, M1i, M2i, and M3i. These are the coordinates of L applied to BI in the B basis. That sentence is really heavy, so we should like pause for a second and let you parse that. I applied my linear map to BI, and then I wrote the result in the same BI basis. Whew. So if I do that exact procedure to all of B1, B2, and B3, then that leads us to a nice matrix expression, which is what I've written on the bottom of the slide here. So if I think of the first column of my matrix as L of B1, the second column as L of B2, and the third as L of B3, then that's equal to the product I've written here. And again, you should always sanity check these expressions by doing the matrix vector multiply. Right, so the first column of the result here is going to be B1 times M11 plus B2 times M21 plus B3 times M31. This is the kind of lecture, by the way, that you should like go home and bond with a little bit. You should, take the slides, kind of look at them, play around, and make sure you understand every equation. I think it's easy to sit back in your chair and kind of let it wash over you, but you should really actively think about all these equations. Okay, so if we put everything together so far, essentially we can think of a linear map as kind of wedging itself in this little factorization that we've written of vectors, right? So if I write a vector in a basis, like V is B1, C1 plus B2, C2 plus B3, C3, then the action of a linear map takes that vector and maps it to a new vector with this new matrix M sitting in between. Now, I think typically in introductory linear algebra class, what happens is this basis here that I keep writing on the left-hand side is kind of implicit. People just write it like that, and that probably gives you the matrix vector multiply notation that you're used to, right? That like, a matrix times a vector gives you another vector. But here, I'm going to be super careful to keep track of the basis on the left-hand side, because our whole point today is to expose our coordinate system as well as possible. Okay, or if we continue in our slick notation, if we think of B as our matrix of basis vectors and C as our coordinates, then our linear map takes a vector that can be written as B times C and maps it to B times M times C, where M, remember, are the coordinates of the images of all the BIs under our linear map. Again, a lot of words going past. You guys should pause, kind of think about this, digest these sentences, and then keep going and post lots of questions on Piazza until you really understand all the details here. So there are a lot of different ways to interpret this expression, and they actually kind of go back to some of the motivation we talked about earlier in today's lecture. In particular, if we look at the right-hand side of the expression at the top of our slide, you can think of parsing this expression in two different ways, right? I could parenthesize it this way. Well, in that case, what is it doing? It's sort of like taking our basis and replacing it with a new basis, but leaving the coordinates alone. Or I could parenthesize our expression a different way, right? I could parenthesize it like that, maybe like that as well. And then what is it saying? Well, now it's saying that I'm going to leave my basis alone and transform the coordinates. Notice that sort of corresponds to those two different interpretations that we talked about of linear maps at the beginning of lecture, right? One is that they transform coordinates of objects. The other is that they leave the coordinates alone, but they're sort of changing the reference point that you're using to view these objects. Okay, so what? Like, why have we bothered to do all of this notation? Essentially, there are a lot of really fast algorithms for linear algebra, and what we're really developing here is a nice formulation that's going to let us keep track of the basis, the coordinate system, and so on for all of our computations. And these sorts of changes of basis are really, really critical in computer graphics. By the way, it's not just computer graphics, it's also computer vision and robotics. In fact, we'll talk about kinematics in a few lectures, which is really a critical topic for robotic arms and these sorts of things that are composed of lots of joints that glue together. So the basic idea here is that, maybe I want to keep track of all these different change of bases, from like the world coordinates to coordinates of your car to, the arm of a person sitting in the car, which is situated in the world, to the hand on the arm on the person in the car in the world, and so on. This idea of change of basis just shows up everywhere. In fact, we already saw it in this course, right? We saw it in our transition from Bezier to B-splines and back. The typical issues from a practical perspective, and by the way, your instructor is terrible at this stuff. Like if you ask me to write code for all these sorts of basis changes in computer graphics, I'll probably get it wrong for a long time. Is essentially bookkeeping issues. So the typical headaches that we have are remembering when to use a matrix and when to use its inverse, and kind of remembering what coordinate system you're in. And that's why the notation that we've proposed in the last couple slides, right, where I really expose the coordinate system as this left matrix here, can be quite useful because it really forces you to remember where you are. Okay, so my high-level, kind of useless philosophical advice here. I think all these, linear operators and so on can get really confusing, but you should think of matrix multiplication as kind of like a little piece of code, right? When I take a vector and I multiply it by a matrix, then what am I really doing? Well, I can think of that functional, right? This thing that takes in a vector and outputs, the matrix times the vector, as like a little piece of code where the input to the code sits on the right-hand side of the matrix and the output is what's coming out of the left-hand side. And so in fact, for example, I do, turns out, kind of advanced computer graphics stuff sometimes, and I'll end up with really annoying pieces of math, maybe it looks like A times B times C times some coordinate X or whatever. I'll actually start writing little arrows like, this is in the hand coordinate system, and then, maybe what comes out of C is the body, and then what comes out of B is the car, and then what comes out of A is the world. And just sort of remembering that a matrix inputs and outputs by going from right to left, I think is a handy way to work out these expressions and make sure that they're correct. And this is both true in your everyday life when you go work at an animation studio or a video game company, as well as on exams and other things. I think these are just really easy things to get wrong. Okay. So we've talked about how to keep track of bases and coordinates, but of course sometimes we need to change our basis, right? So maybe I want to think of objects relative to a new basis point, for example. So remember how we represented linear maps, right? We applied the linear map to our basis, and then we took the result and wrote that in the basis again. Let's say that I have two bases, A and B now. So now I want to go from one to the other, whereas our previous example only stayed in one basis. And moreover, now I'm going to take all of the basis vectors A, and I'm going to write them in the B basis. Right? So like AI has these three weights as a linear combination of the B vectors. Then you can take this expression here, stack it together. Remember that A is like A1, A2, A3. Similarly for B, and M is the matrix whose entries are these values. Then essentially, by combining these relationships in the first equation here, I get this nice matrix expression on the slide. If I multiply both sides of this expression by the inverse of the matrix M, then that gives me a way of writing B in the A basis. Okay, So now let's say I want to do a change of basis. Namely, I have a vector v in the b basis, and now I want to get the coordinates of v in the a basis. Right? Remember, this object is the coordinate. Well, here I've just taken two expressions from the previous slide and copied them at the top of this one. The basic questions we might want to ask are, what are the coordinates of v in the a coordinate system? Okay, so in order to do this, we're going to apply the same linear algebra sleight of hand rather, that we've already applied in other lectures in this course. So namely, we can write v as b times our coordinate vector c, and I can always multiply it by a matrix and then its inverse as many times as I want. Now remember that eventually what I want is that I want this to be a times some new set of coordinates c bar. And then the question that essentially we're asking are, what is that c bar vector? Or that c bar set of coordinates. I already got it wrong. Okay, so I want this to be a times something. Well, one thing I could do is be kind of a smarty pants about it and just cancel the a out. I'm going to take a, multiply it by a inverse, and then write b times c. Now notice that that's obviously valid, right? All I've done is taken the first expression and multiply it by the identity matrix in fancy notation. Okay, but now if I group this expression, oh no, that's not quite what I wanted to do. Okay, so I could have done that, but let me tell you where I went wrong. You can see your instructor fixing themselves live. This A inverse doesn't really make sense because this A contains geometric objects, right? It contains vectors. This is why this kind of pedantic notation is actually throwing me off. I usually don't bother. But the motivation is still the same. I have that I want to write V as a combination of the vectors in A. So I know that my goal is to write it as A times something. And what I should have done, my apologies, is remember that I have this expression at the top of the slide. Amusingly, I now remember I make the same mistake every year I teach this course, and on video that's no different. So this expression on the top of the slide does make sense because M is a matrix of numbers, so I can invert it. And I know that I want A on the left-hand side. So these things fit together nicely, right? I can write, well, I know B is equal to A times M inverse times C. So if I factor it that way, I just found the coordinates in the other basis. Oof, sorry about that. Okay, and so that's what we've written here. And so this is another advantage, at least when you do it correctly, not when you make a mistake like I do, of keeping track of the coordinate system on the left-hand side, is that essentially you can figure out these change of coordinate equations by just plugging in expressions that are very easy to either remember or to derive by hand pretty quickly. Okay, so far we've basically done everything formally, right? We're writing a bunch of symbols, but you might remember from linear algebra class that there's lots of nice geometric interpretations of linear maps, especially in low dimensions. So the question that normally, if I were teaching this class live, we'd take a survey and pause for a moment. But instead, I'm going to ask, pause for a moment for you to answer in your head, and then we'll go back and check. Let's say that I have a linear map specifically applied to R3, right? Vectors in 3D. The question is, which of the transformations on the slide here geometrically is linear, right? The identity map being one that leaves things alone, translation, shifting things around, rotation is rotating them about the origin, scaling, and so on. So which of these maps is linear? The answer is all but one. Now remember, at the beginning of our lecture, we motivated a particular property, namely that L, that was supposed to be an L, that our linear map applied to the zero vector has to give us the zero vector. And I claim that one of these images on the bottom violates that property. That image is here. Because notice that the origin moved. So translation, unfortunately, is not a linear map. But translation is a really critical way to compose a 3D scene, right? I mean, we don't just want a big jumble of objects all sitting at the origin. We need to translate them around. So we have two different options, both of which have appeared in historical graphic systems for how to do that. One would be to keep track of translations separately. That becomes a humongous bookkeeping headache. Or we can essentially use a new little piece of linear algebra we're going to develop next to keep track of translations in the same formalism we've already developed. Incidentally, one last way to remember why isn't translation a linear map? Well, linear maps are things that apply to vectors, at least so far, the way we've talked about them. And translation isn't a thing that you can do to a vector. You can scale a vector, you can add them, but you can't really translate them. Okay, so from that last perspective, this leads us to talk about points, right? Remember, points are locations in space rather than displacements. So we can do things like add vectors together, but we can't do things like add points together or scale points or anything like that. Although we could add a vector to a point, right? That's like displacing the point. Okay, so that's going to lead us to a slightly different space than a vector space, because now we need an origin, right? We need a way to specify points in 3D space. And that leads us to a different mathematical setup known as an affine space. And so points are members of an affine space. Vectors are members of a vector space. And in this class's notation, we're going to put a tilde, a little squiggly, on top of points. So remember that points are members of affine spaces, and we're going to be able to think of them like extensions of vector spaces. Now, we're going to use a bit of a notational sleight of hand to keep track of points. We're going to cheat a tiny bit for elegance. Namely, we're going to decide that if I take a point and I multiply it by the number 1, I get that point back. So just bear with me a little bit. I know that's cheating a bit. So I can think of a point as the origin plus a displacement, right? That's the sort of picture that we keep drawing, right? We think of the origin, and then, a point is like displacing along the different basis vectors like B1 and B2. So in that case, I can always write a point as the sum that I've given you here. Now, continuing in our matrix vector multiplication notation here, I'm going to make a new matrix, which is an extension of that previous one. Remember, we had that matrix B before, which was just this piece. Now I'm going to add a fourth column, which is the origin to my sort of abstract geometry matrix here. So if I do this matrix vector product, remember it's left to right on the first term, top to bottom on the second, what I'll recover is this sum here. So this gives me a nice notation for writing this point P tilde. And essentially I can think of P tilde as being in a 4-dimensional vector space where so far that fourth coordinate is always going to be 1. We're going to see why we might want to let that change later, but for now we're just going to leave it as 1. And this is going to allow us to continue to have this nice coordinate notation with just a new matrix on the left. So we can do all kinds of nice things, right? We can take 2 points and subtract them and get a vector, right? That makes perfect sense geometrically because the difference between 2 points is the displacement. I can add a point to a vector and get a new point. And so we're going to keep these two things in mind as we motivate some of the algebra that we'll do in this new notation. So we defined a matrix F. Remember that F had B1, B2, B3, and then the origin. And we can call that an affine frame. Essentially, the frame is an origin plus a basis. So that way I can describe any point as the origin plus a displacement. And so this allows us to continue to use coordinates, not just of a vector, but also of a point. So here's our recap so far. We're going to write vectors in a basis, right? I can write like v equals b times this coordinates here. And we have this nice change of basis formula that I got a little wrong on the first time. And I can also write points using similar notation. I'm just going to add a dummy coordinate of a 1 on the end here. Now, we're going to see that this notation is really nice because it's going to allow us to actually talk about all kinds of different transformations, not just scaling and rotation, but also this one that was missing from our linear transformation list, namely translation. And let's see if we can motivate that a little bit. Okay, so here we have an expression p tilde equals f times c. And so just like before, if we want to talk about an affine transformation, it's going to look like a linear transformation did before. Remember, linear transformation, I had my kind of basis matrix on the left, I had my coordinate matrix on the right, and I could think of my transformation as sitting in between. Right? Let's remember, I can read this symbol as maps to. I can do the same thing for affine transformations, but now I'm working in this 4-dimensional space. So an affine transformation takes this form. For now, we're going to always think of that last row as 0, 0, 0, 1. And we're going to see that that's actually enough for most of the operations that we need. And then when we talk about camera transformations, we're going to allow that last row to change. Okay, so first of all, why do I want that 0, 0, 1 there? Well, my affine transformation needs to take points and map them to points. So one thing that you should check is that when I take the coordinates of a point in this 4-dimensional space and I apply that sort of general matrix M to it, what's going to happen? Well, I need for the last coordinate to remain a 1, or else I've broken the rules, right? The rules are that if I want to represent a point, the last coordinate needs to be a 1. Yeah, and indeed, if I look at the last row times our vector here, notice that it basically zeroes out x, y, and z. I'm just left with 1 times 1, and I get a point back. So in other words, a matrix of this form, the reason why that last row looks the way that it does is so that we take points to points. Similarly, we need to take frames to frames, and so in order to do that, we need to make sure that we have vector, 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 point, and when we apply M, the same thing happens, and I'll let you convince yourself at home that that is indeed the case. Okay, so we already know how to apply linear maps to transform a vector basis. So now if I have a point, essentially I can still use my linear map, and the way that I'm going to do that is by saying, well, a point is the origin plus a displacement. So a linear map is really a thing that just applies to the displacement, right? Like if I'm talking about rotating an object, like taking this little square and rotating it to, I don't know, some other square. In order to do that kind of a map, I'm leaving the origin alone, and I'm just messing with the displacements. And the way that I can accomplish that using this 4x4 matrix is to just insert my linear map in the upper left 3x3 block. And you can convince yourself at home that really this has the effect of applying that linear map to the basis and leaving the origin alone. How would you convince yourself of that? Actually do this giant product here. But we can do more than just linear maps. We can also carry out translation. This is where things get kind of cool. So remember that it makes perfect sense to talk about the translation map, right? The map that takes a point and adds a vector to it. So in general, in this class, if you're ever not sure what to do, you should take vectors and write them in a basis. It's just like a good thing to try. So in particular, I'm going to take my translation vector t and write it in the B basis. And so if I do that, maybe I'll use this suggestive notation with the 4s sitting on the end. And one thing that you can do is actually say, let's say that I want the linear map, which takes P and gives me back this point, which is P plus T. Okay, so if I do that, I can actually represent that using a very specifically chosen matrix, which I've given you on this slide here. Okay, so what's going on here? Notice that the upper block, the upper 3 by 3 block, is just the identity matrix. So in other words, we're leaving the basis alone. The only thing that we're doing is we're shifting things. Okay, so let's actually do the matrix vector multiply here. So what happens when I multiply the first row by our vector here? Well, I get 1 times C1 plus 0 times C2, 0 times C3, plus 1 times M14. So I get C1 plus M14. If I do the same thing for the second row, I'll get C2 plus M24, C3 plus M34, and 1. So take a look at what happened. It took the original point, whose coordinates were C1, C2, C3, and it mapped it to a new point, which was shifted by M14, M24, M34, but this is exactly the coordinates of our translation vector t. So in effect, this matrix that I've written here is a new motion that allows for translation in this cool 4x4 coordinate system that we've written down. Now, in general, we can combine these different operations together, and that is going to lead us to this just generic affine matrix that I've written for you here. Okay, and so in general, this 4x4 matrix can rotate, scale non-uniformly, and translate depending on where the interesting information is. If the interesting information is in the fourth column, it's translating. If it's in the first 3 columns, it's rotating and scaling. Isn't that cool? I think that's really cool. Essentially, this is a way to kind of patch up a hole in linear algebra, right? Linear algebra doesn't know how to translate because it works on vectors and not points. So the way that we're going to do it is we're just going to add a fourth coordinate for points and extend linear algebra to 4x4 matrices. And in fact, it gets cooler than that. So let's say that I have 2 points, p tilde and p tilde. I have 2 points, p tilde and p tilde prime. Now remember that if I take 2 points and I subtract them, I get a vector. We'll take a look at what happens if I take the coordinates of p tilde and p tilde prime and I subtract them. What I get, I think you guys could all do this arithmetic at home, is this vector here, right? C1 minus C1 prime, C2 minus C2 prime. But that last row is 1 minus 1, or 0. Now remember that the difference of 2 points should be a vector. And so this notation actually suggests that I can represent vectors as objects whose last coordinate is 0. And in fact, that makes sense, right? So for example, if I return to this little factorization here, notice that if I put a 0 in this last element, that would essentially be like getting rid of that origin point, and what I'd be left with is just the sum of vectors, which is another vector. Similarly, remember that if I add a point to a vector, I get another point. And indeed, that makes sense, because in our last coordinate, we'll get 1 plus 0, which gives us 1. So we actually have a totally consistent piece of notation, which is really neat. This is a way to deal with both points and vectors and keep track of which one is which, essentially by keeping a little binary digit at the end of our vector. Vectors are not affected by the translation part, which makes sense because vectors are not affected by translation. So if I apply a matrix like this 4x4 guy that we've written here, essentially the 0 is going to zero out this entire last column, which is exactly what should happen, because if I apply an affine transformation to a vector, the thing that only affects points shouldn't be kind of noticed. Okay. And so that's the basic point here, that essentially by adding a fourth coordinate, where the coordinate is 1 if I'm a point and 0 if I'm a vector, allows me to have a consistent picture of linear algebra that deals with both points and vectors at the same time. Now, eventually, we're going to have to talk about hierarchical modeling, and that is going to compose many coordinate systems together. So again, if we return to this car example, I probably want to model the fingers of the hand and the coordinate system of the hand, and then place the hand, the coordinate system of the arm and the coordinate system of the body, and so on. And this is going to allow us to nest all of these transformations together, basically just by multiplying a bunch of matrices. So for example, if I want to rotate the wheel of the moving car, maybe you have this new rotation matrix, and I'll let you think a little bit at home exactly where to place it in this chain of matrix multiplies that takes you from world to car or vice versa. So in order to think about these sorts of problems, we need to ask the question of how to combine transforms together. And so that's going to be the last little bit of our lecture before we introduce homogeneous coordinates. And essentially, the main answer to this question, how do you combine transformations together, is carefully. And the reason why is that ordering matters here. One thing you might remember from linear algebra class is that matrix multiplication is not commutative, meaning that A times B is not equal to B times A for matrices. In fact, you can see that geometrically. So here I'm giving you, these are affine matrices working on the plane. Remember, the plane is two-dimensional. So an affine matrix will be 3 by 3 to handle that translation part. So like here would be the vector piece. Here would be the affine piece. So let's say that I want to scale and then translate a point. Well, remember that matrix multiplication goes right to left, right? Because like the vector would go on the right of the matrix. So if I want to scale, I should put that here. Notice that this matrix scales by 2, 2, and it leaves the translation piece alone. Now, if I want to translate by 3, 1, that is a new matrix here with where the information is in that last column. And if I multiply these two things together, then I'll scale and then translate. Notice, again, this is the most common source of bugs in code in this area. If I want to scale and then translate, the scale goes on the right-hand side and the translate goes on the left. Okay, so the ordering flips backward just by nature of matrix multiplies. And if you don't do that, you'll end up with a bug in your code. So for example, let's say that I scale and then I translate, or I translate that and I scale and I apply that to this little rectangle here. You can see that the results of these two chains of operations is not the same. Again, this is the #1 source of bugs. And in fact, if I actually do the matrix multiplies, I'll get two different matrices, right? These are just not the same operation. And so essentially, when we write code for composing these transformations together, we're going to have to be super careful to keep track of the ordering and the chain in which we have to apply the transformations between the different coordinate systems. Okay, so hopefully now you guys at least see the high-level value of adding an additional coordinate. So if I'm in the plane, I'm going to have 3 coordinates, right? Where that last coordinate is 1 if I'm a point and 0 if I'm a vector. And if I'm in 3D, I'm going to have 4 coordinates where, again, that last extra coordinate is useful just to keep track of objects that are points versus objects that are vectors. And the term for adding sort of a dummy dimension to my linear algebra to make math easier, the fancy term for that is something called homogeneous coordinates. And homogeneous coordinates is essentially this practice of adding one additional object to the universe. And in fact, homogeneous coordinates are not just useful for distinguishing points and vectors, they also have another really critical application in the computer graphics world, and that's for perspective projection. So remember that, like, if I'm rendering parallel train tracks, you know, here's my camera, I'm looking out in the world and I'm standing on train tracks, hopefully not active train tracks. You know, here's the sky. Your instructor is not an artist. You can see that. There's the line. And, you know, here are my feet. Then if I'm standing between train tracks, then as they go farther away, they appear to go into one another. This effect is called foreshortening. And it's essentially, we're going to see that that the homogeneous coordinates are going to allow us to take coordinates in 3D where these train tracks look parallel, and then give them coordinates on the image plane where they don't look parallel. This is a thing that linear algebra can't do, but homogeneous coordinates can. So in order to do that, we're going to need a little bit more math. Namely, we're going to introduce the homogeneous coordinate system. Now, in general, I'm going to say that a homogeneous coordinate, like for example in the plane, is where I have the usual coordinates like x comma y, and I'm just going to add a third one onto the end, and I'll call it w. Now in 3D, essentially everything is going to carry through the same way, but I'm going to have x, y, z, w instead. But I'm going to do a trick, which is I'm going to say that I identify points x, y, w, and points cx, cy, and cw for any non-zero scalar c. Okay, so the word identify here is a little bit weird. Essentially what it's going to say is that I'm going to say if 2 points can be written as scalar multiples of one another, we're going to call them the same point. This is really a topological term, but we're not going to worry about the mathematical details much in this course. We'll see that in practice it's actually pretty easy. So for example, let's say that I wanted to convert a point x comma y to homogeneous coordinates. Well, that's a pretty easy thing to do. I could write it as x, y, 1. But the kind of weird thing about homogeneous coordinates is that they're not unique. I could also write it as 2x, 2y, 2, or even minus x, minus y, minus 1. All of these are homogeneous coordinates for the point x comma y. Similarly, let's say that I have a point in homogeneous coordinates and I want to write them in standard coordinates. Well, in standard coordinates, we're going to assume that the last one is 1 by convention. Okay, so what does that mean? Well, it means that if I'm already in this form, then the standard coordinate is really easy. It's just get rid of that. Now, let's say that my last coordinate is not 3. Well, then I'm going to convert it into a form where the last coordinate is 1, and then I'm good. So one way that I could do that is divide everything by 3. So 12 divided by 3 is 4, I think. Minus 6 divided by 3 is minus 2. 3 divided by 3 is 1. These things are equal to one another because remember in homogeneous coordinates I can scale by any scalar that I want. So that leads us to the point 4 minus 2. Similarly here, maybe I scale everything by minus 1/5. Then I'll get minus 1, minus 3, 1, which leads me to the point minus 1, minus 3. Hopefully I did that right. Minus 1, minus 2. Yep. Okay. So you can see that it's really not so hard to convert things to homogeneous coordinate and back out, right? So if I want to convert to homogeneous coordinate, the easiest thing to do is just stick a 1 on the end. And if I want to convert away from homogeneous coordinate, I first normalize by dividing by that last coordinate and then throw away the 1 that's sitting there. Okay. So in 3D, it's basically the same. We're just going to use 4 vectors and 4x4 matrices. And in 2D, we'll use 3 vectors and 3x3 matrices. That last coordinate is some value. Actually, I think the word arbitrary here is not really right. But it's a value w that I can use for a scale or a weighting. Okay. There's all kinds of interesting ways to think about homogeneous coordinates. They can be used to express points, but they can't really be used to express vectors necessarily. That's where things get a little bit tricky. Because, like, let's say that I had a vector, x comma y. Well, using the previous part of the lecture, I might be tempted to write it in homogeneous coordinates as x, y, 0. And indeed, that would be kind of a reasonable thing to do. Notice that this cannot be interpreted as a point because I can't divide by 0. But what I can do is scale by any non-zero constant. So this is sort of the same as cx, cy, 0. So the best that I can do is I can't keep track of vectors, but I can keep track of directions. So like a vector up to scale. Fun aside here for math students in this course. Again, I encode points and directions. So a direction is kind of like a point x comma y comma 0. And if you want to interpret all of these things together, let's say that I take a point and I just start moving in that direction farther and farther away from the origin. Okay? So how could I do that? Well, I could say, maybe here's x, y. So if I want to move farther and farther away from the origin, I'm just going to multiply it by some giant c. Now in homogeneous coordinates, that's the same thing as writing x comma y comma 1 over c, right? Because I can scale things. So if I take c off to infinity, right? So I just kind of keep moving farther and farther out in this direction. Eventually, my homogeneous coordinate somehow approaches this point x comma y comma 0. So I can think of directions as sort of like points off in the horizon, like I'm scaling points farther and farther and farther. Now, if you really want to make your brain explode, I could have done the same thing with negative values of c, and then I would go off in this direction. But in fact, I can identify minus x minus y 0 with xy 0. So a really crazy thing happens in the homogeneous universe, which is that if I go far enough out in one direction, it actually wraps around on the other. If you're a math student, you might be tempted to think about the area of topology, and you would not be wrong. So I'll let you think about that. So in any event, if that's not important to you, I wouldn't worry about it. So why use homogeneous coordinates? So for one, it allows us to distinguish between points and directions, not points and vectors, but that's kind of convenient. And so we can use homogeneous coordinates to write down like matrices of translations and scales and so on. Homogeneous coordinates also allows us to do a really cool thing, which is specific to computer graphics. It's kind of magic that this nice sort of confluence of math and computer graphics happens. And that's that it allows us to do camera transformations. So here's going to be the trick. Let's say that I'm rendering a fish, like the fish on the screen here. Now, in general, when I'm drawing a 3D universe, I can kind of think of there being like a little square in front of my eye, which is going to be like the image that I'm rendering. And really what's going on is that like here's my eyeball on the left-hand side of the scene here. And maybe here's the image that I'm rendering. It's kind of like a little screen door sitting in front of my eye. And then I can send a ray from my eye through that screen door out into the universe. And the first thing that it hits into is the object that I'll draw, right? Eventually, that's more or less going to motivate the ray tracing algorithm that we'll talk about. So what does that mean? Well, what that means is that, this square essentially gets bigger and bigger and bigger the farther that I move from the camera. So in order to get the position on my screen, like maybe my screen is here, this is 0, this is 1. What am I going to have to do? Well, I'm going to look at the depth of an object from my eyeball and notice that the width of my screen gets bigger the farther I am from the camera. So I'm going to need to divide by that coordinate in order to get the position on my screen, which is sitting maybe like just by convention 1 unit away from my eyeball. Okay, so here is a sort of simpler picture from the top down. So here's my camera looking out into the world. So maybe here is my computer screen. And I maybe just abstractly think of my computer screen as sitting at z equals 1, where z is like the distance from my eyeball. Then the farther that I move out, the wider my field of view is. So if I want to figure out where a point is on my screen, I have to do a little bit of math. Namely, Let's say that, by the way, in this slide, we're ignoring y, like the up and down. So think of like I'm looking down on your eyeball and it's got a view going out like that. Okay, so let's say that I have a position x comma z, and it's in 3D space somewhere, and I'm trying to figure out where it is on my screen, which is sitting at z equals 1. In that case, I have to draw a dotted line, well, it doesn't have to be dotted, I suppose, from my eyeball to the object in the scene, and I want to figure out its intersection with the screen here. And in fact, what you'll find is that that point is nothing more than taking the coordinate and dividing it by the depth. So let's write this in slick notation. The projected point in our homogeneous coordinates is x comma z. Maybe we haven't really talked about the y coordinate. Maybe we'll just leave it at 1 for now. This last coordinate here is just for convenience. Oh, I'm sorry, I misspoke. The x over z is the horizontal position. This 1 here is because it's at distance 1 from the eyeball. And this third one is just the homogeneous one, right? So in the previous slides, this is x over z, comma 1, semicolon 1. But remember, in projective coordinates, I can scale by anything that I want. So what can I do? I can take this previous vector, it's kind of annoying, it's got a division in it, and instead I can write it as x comma z, right? By just scaling the vector by the z value here. And these are projectively equivalent vectors. It's a fancy phrase. Okay, so why would I do that? Well, what is this vector? I can think of it as a matrix times the coordinates of my original point, right? And that matrix is essentially going to take, what do I have to do? I need to replace that 1 with a z coordinate. And one thing you can convince yourself is that this is the matrix that'll do that, right? Again, anytime I use a phrase like that, you should actually do the matrix vector multiplication and convince yourself that it's right. So what does that mean? That means that secretly camera projection, which has a division in it, so it's kind of weird, but in homogeneous coordinates specifically, camera projection is actually linear. It's given by a matrix, right? Or I guess affine maybe is the right word. And the reason for that is that essentially the projective scaling is taking care of this division by z. Isn't that sneaky? So essentially what happens in computer graphics code is we often do all of our computations in these homogeneous coordinates until the very last step when I need to actually compute the position of a pixel on the screen. And at that very last step, then I divide by w and actually have the real position. I mean, at some point you do need absolute coordinates, but not until the very end. And so essentially that division by w is doing exactly the same thing as just accounting for the fact that your field of view gets bigger the farther you are away from the camera. And so this is the real showpiece of this homogeneous coordinate system. Essentially what it gives you is that projective equivalence is just given by this nice division operation at the end of the day. And so we're going to practice with that a lot in this course. You're also going to do it in your code. But essentially that's the really beautiful thing that comes out of today's lecture. So to recap a little bit, we started by talking about vectors and introducing a bit of notation where we write a vector specifically in a basis by keeping an extra matrix on the left-hand side, which is the basis matrix. Then we noticed that if we add one more column to that matrix, we get an object called a frame instead of a basis. And the frame includes those basis vectors as well as an origin point. In doing that, we saw that we ended up writing vectors as coordinates that end in a 0, and we wrote points as coordinates that end in a 1, right? And that was essentially to turn on and off that last column of the frame matrix, which was the origin point. But we also noticed that we could do lots of arithmetic on those vectors. We could add them, subtract them, and sort of have a consistent picture. This led us to this idea of homogeneous coordinates, where we take all of our coordinates and add an additional dimension just for convenience up to scale. And the really beautiful sort of thing that happens is, in addition to continuing to allow us to do everything we already discussed, it also allows us to do one more extremely important thing in computer graphics, which is to convert between coordinates in the 3D world and coordinates on the screen, which requires dividing by depth. In our next lecture, we're going to talk about composing these transformations together, and then we're going to talk about one last transformation that we'll need, which is how to transform normal vectors to surfaces, which we're going to need for rendering. But with that, we'll call it a day, and we'll see you next time.